You are listening to EE Times On Air, and this is EE Times Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Professor Rodney Brooks talks about the evolution of robotic technology, past, present, and future. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny will be talking robots with Emeritus Professor Rodney Brooks of MIT, currently CTO of Robust AI, which he co-founded in 2019. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Rod Brooks has been a force in robotics since the 1980s when he first started to question the status quo of top-down, planning-based AI in favor of more biologically based approaches. In 1990, he issued a rallying cry for a new generation of roboticists in the form of a paper called Elephants Don't Play Chess. Since then, he not only rose to be head of the Computer Science and AI Lab at MIT, but also founded iRobot, Rethink Robotics, and Robust AI, which have produced the Roomba, Baxter, and Carter, respectively. There are links to Brooks' work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. I met Rod at Robust AI in San Carlos, Silicon Valley. Rod Brooks, welcome to Brains and Machines. So you've had a very long and distinguished career as a roboticist. I've known you for at least 30 years of that. Can you start by just giving us, from your own point of view, a flavor of your contribution as you see it?
One way of looking at it is I started out life as a pure mathematician and I became a vacuum cleaner salesman because one of my companies came up with the Roomba. That was a practical robot, which we sold 50 million of. But I've been a professor of artificial intelligence back in 1977 in Australia. I wrote a really bad master's thesis on machine learning. Then I came to Stanford and did a PhD thesis on computer vision. 4 years, mainframe computer, looked at 3 images because it took 2 weeks to process each one back then. And then I went to MIT and was on the faculty there for a long time working on robotics, artificial intelligence, artificial life, and thinking about how to build systems that could work in the real world, which is how I came to build the Roomba as a real world application of that. Rather than just theoretical things, I've always wanted to test the ideas out in the real world.
One of the things I always liked about your work at MIT was that it was very practical and it was very bottom-up. And you started what is now known as behavioral robotics. Can you tell us a little bit about that?
When I started, which was very early days of mobile robots, people were trying to build a three-dimensional reconstruction of the world, the way they do now, but back then it was really hard to do. By sensing the world, building a three-dimensional reconstruction, then planning in that reconstruction what the next move was, and then slowly executing it. And it took mainframes way less than real time. I've been helping out Hans Moravec as he was finishing his PhD thesis, and the robot could move 10 meters in 6 hours at night when no one else was using the computer. And insects with only 100,000 neurons were flying around, chasing each other, attacking other insects, and doing all sorts of things with 100,000 neurons. Okay, something very different is going on inside those insects. So then I started thinking about what that might be like, and the behavioral approach started out with building simple couplings between sensors and actuators, and then putting more parallel layers of stuff which modulated the simpler behaviors to get more complex behaviors.
It's very interesting because in neuromorphic engineering, there's always an assumption that you're going to have little neural circuits that are going to perform behaviors, and then they'll collectively work together to perform longer term, more strategic, more complex behaviors. So I think that was one of the reasons I thought your work was so interesting, was it fits into that very nicely. And it comes under the category of reactive systems, yes?
These systems were very reactive because I always wanted to put them in the real world where people were walking around, where other things were happening. And they couldn't afford to compute for a long time before they moved. They had to react to the frequency of the real world. So they were reactive. And some people got so stuck on the reactivity that they would say, well, but it can't play chess or something like that. And no, it wasn't designed for that. It was the stuff that comes before those intelligence layers, if you like.
Another thing I remember from one of your first big famous projects, which was COG, you were very interested in the idea of using physics to compute where compliance, for instance, was necessary. So rather than having to give some computer a job to do, which it was going to do too slowly and not well enough, you would just let the physics of a spring do its thing. So I know you had a student working on that. Was that something that you were strongly interested in at the time, or was it just incidental?
So let me talk about COG a little bit. A lot of people thought COG was a real diversion for me because previously I'd made the joke I worked on AI, artificial insects, things at that level. And then suddenly I started building humanoid robots in 1992. I didn't want to spend my whole life on one thing. I wanted to see what we could do with the human form. And I knew from my much earlier work in robotics that when humans do something in the world with their hands, it's not just controlling position. It's feeling forces and reacting to those forces. And when we learn a new physical skill, we're essentially learning a little, well, you might call it finite state machine. If you feel the force this way, do this thing. If you're in this state and you feel that, do that thing. So you can do things blind. And I like to think in the now, a prime example of where position control, just moving by position, just doesn't work, is shucking oysters. If you've ever tried to shuck oyster, make sure you wear the glove on your left hand. And then you've got this knife and you're pushing in and you feel where the little crack is and then you twist and it takes a little while to learn, but after a while you get really fast at it. But it's not something you could just show a robot. Lots of examples of the positions your hands went through for 10,000 oysters because you use the different strategies for different oysters and every oyster is different. And so you're never going to learn it that way, which, by the way, is the mistake all the humanoid companies are making right now. But I knew that applying forces and measuring forces was important. And it was actually two people in the bigger artificial intelligence lab, Gil Pratt, who's now chief scientist of Toyota worldwide, and Matthew Williamson, who did his master's thesis with Gil and then came and did his PhD with me, invented something called series elastic actuator, where there was a motor and a spring in series with the load. And by measuring the deflection on the spring, you could measure force and you could control the amount of force by controlling the torque on the motor. So you can both measure and control force. And so we put those into a set of arms that Matt Williamson built for his PhD thesis on the robot COG. And then he showed how with fairly simple feedback circuits around that, we could get these arms to do all sorts of things which were considered hard to do. Give it a crank and it just plays around and pretty soon its little almost neurons get into sync with that and it can turn the wheel around. Or play some music and detect the beat of the music and give it drumsticks and a drum and it starts playing in synchronization, playing the drum with no change in the code. It's just what the inputs are and what the outputs get changed. So it's synchronizing messages in these sort of neuron models. Now, we were simulating them with a digital approximation using conventional computing to do that.
Retrospectively, do you look at that as being almost like central pattern generator?
Oh, we talked about CPGs. Yeah, that was very much in the literature that we talked about. There were other things we did with COG, and Cynthia Brazil was the main person there, where we realized that people interacting with COG led it, even if they were not consciously leading it. Because we react to things with big eyes in a certain way. We do baby talk with them. We just do it. We're hardwired to do it. That's how we drag our kids along through learning. Every parent thinks their kid is smarter than they are, but that's important because they then expose them to the next thing that they can't do yet, and they provide scaffolding for that, and then the kid is able to learn it. So we were computer scientists, or AI or roboticists, and we were talking to everyone across campus in all the disciplines.
In an essay you wrote in 2018, you were skeptical about the use of artificial neurons, let's be general that way, in control tasks, because at the time they weren't being used very much. And you weren't sure whether that was going to happen, or at least that was my impression. Can you talk about where you see artificial neurons as fitting into robotics these days?
Let me answer a slightly different question. I was skeptical about the learning of weights in linear perceptrons when there's perfectly good control theory with mathematics, and you can build for a lot of mechanical systems things that work very well. There's been a fetish around reinforcement learning that we just start with a blank slate and the thing will learn everything. And some people have had robot arms just whacking around in the world, hitting things, and after many hundreds of hours, they learn to do, in a very wobbly way, something which we could already do with a pretty simple control algorithm. I was skeptical of that. I'm skeptical today of people trying to teach humanoid robots by demonstration. And in some places, there are armies of people with things attached to their fingers and hands, and they're doing some task, and it's recording all the emotions and recording the images, feeding that into various forms of deep learning, sometimes with the generative step, all those sorts of things, and saying, this is the way we're going to get general intelligence. But I think, unfortunately for all those companies, they're a little naive in that they're doing everything on position control. And that's not how we do stuff. And it's really hard to both measure the forces that a person is applying and measure the forces they are sensing. If someone figures out how to do that, maybe they'll come up with a valid learning strategy. And maybe they can build something that's useful with artificial neural networks, linear perceptrons, essentially. Maybe they can, but it seems like they're spending lots of billions of dollars right now on that. And I'm a little skeptical. I actually started a company and built humanoid robots for many years. I put about 5,000 humanoid robots, upper body humanoids, into factories. The robots were called Baxter and Sawyer, and the company was Rethink Robotics. They used series elastic actuators, and Matt Williamson came and joined the company for a few years. And we could do stuff in factories which are harder to do with a conventional robot. We didn't do a good job of really telling people how they should use them, and they tried to use them in the old way. What we did end up doing is we let industrial robots out of the cage, and they used to always be in cages. Now when you go to an industrial robot show, they're out of the cage because people using that technology have figured out how to make them safe because they can feel an unexpected force. So that was the ultimate contribution they made, even though I was going to use humanoid robots for much the same rhetoric as the current humanoid companies use. Well, the world is made for humans, let's use human form. But I did that for 10 years, produced thousands of robots, and I think it's a dead end.
Before we move on, can I ask you about Boston Dynamics? Because I believe it was started by a colleague of yours at the AI lab at MIT. Boston Dynamics, which has to have the most famous robots in the world. I'm afraid I think Big Dog is probably the most famous robot in the world. What do you think about that work? To me, it looks a little bit from the outside like a lot of fantastic physicality, but not so much situational intelligence.
Mark's a good friend. I still see him quite often. Mark Rabert, he left the lab in 1992 and started the company Boston Dynamics. Within the lab, he'd had a sub-lab called the Leg Lab, which Gil Pratt then took over, and that's where Gil Pratt and Matt Williamson invented the series elastic actuator. And Mark's work was very similar in a way to the sort of thing I was doing. He started with a very simple hopping machine, one leg, but it didn't hop in 3 dimensions. It lay on its side on an angled piece of wood, so it could only fall over front and back. It couldn't fall over left and right. And then after it got little control algorithms that did that, he had another set orthogonal to that, and then he had a 3-dimensional hopper, and then he put 2 legs together. And so he was very much building up these simple control loops from very primitive physical systems which didn't know precisely where they were in the world. And then he went off and started his company. He eventually got funding, and he made, yes, they're famous robots, but there's 50 million Roombas. Professional competition here, please. And Mark has always been honest if you ask him the right questions, because the videos just shocked people how good they were. But then at a conference, if he was being interviewed on stage, people in the know would say, so how many takes did this one take? And then he'd say, 28 times before it worked. I think people overestimated the competence of the robot from a single performance, which is all they saw in the video. And people got too excited about those robots. There were stories close to 20 years ago. These robots are going to replace all jobs. It's the same hype cycle that always happens. This is amazing. How can it do that? It must be really intelligent because it can do a backflip. So great work. But the inferences people made from it, I think, were wrong.
Okay, so the Gray Walter conference, I think it was about 20 years ago, you said there might be something in this neuromorphic stuff, which I believe was your reaction to a comment or some discussions you'd had with Andreas Andreou. I want to see 20 years later whether you still think there might be something in that neuromorphic stuff and how you feel about this field.
I'm skeptical that what we think of as computation today is the right stuff. I suspect there's some combination of physicality, both in the world and physicality in the control system. So those springs were really good. I mean, certainly, if you look at all the humanoid walking robots, they don't walk like humans because they don't have springy systems. And you don't want to be near one of those humanoid robots when it's starting to fall down, because its only way to balance is to apply a lot of torque very fast. And if it really is falling and you're in the way, you will get hit by a really strong metal leg with no compliance. So I think from the way we couple into the world to what is going on in the head, if you like, the stuff that's the control, which may be a mixture of the physicality of the materials in the legs, of the electrical signals and how they work. It certainly doesn't seem to be digital in the sense that Turing came up with digitality, simulating a human computer, calculating a number one digit at a time, and our computers are based on that analogy. So certainly I think in the long term, there could be a lot of stuff there. Can I give you an example of where the wrong kind of stuff maybe? I use this in talks. I say to people, remember when Elon Musk wanted to put things into orbit? Did he just write a Python script and say he was done? No. He had to build rocket engines. He had to burn fuel really fast. He had to worry about aerodynamics. He had to do all sorts of stuff to get things into orbit. And the audience, especially if they're computer nerds, yell at me and say, but it does a lot of computation. He did a lot of computer simulations, and there's computers in the rocket. Yes, there are computers in the rocket, and yes, he did use computation. But you can't get the thing into orbit just by sitting and computing. You have to burn rocket fuel. We in AI, we in the world, we in the VC land, think it's all just computers in our heads. We think we can simulate anything. But the simulation for a rocket is different from an actual rocket. And it's really hard for people to think about this because it's become so ingrained. Is simulation of what goes on in the human head and the human body the same as what goes in the head and the human body, produce the same result? Or is it like a rocket where you can simulate all you want, you still won't get into orbit? And it's a really hard thing for people to think about because computation has become so embedded in our understanding of the world.
In fact, that was something else that came out through the 90s with people like Barbara Webb using robots to create simulations of what we thought the neural pathways were doing in insects, rather than just doing simulations because you couldn't sufficiently replicate the physics of the world at that time. I think that's an important principle, is that simulation only takes you so far. And then, of course, you have to build things in the real world if you want them to act in the real world. Another thing I wanted to ask you is behaviors, whether they're implemented with code or some kind of neural system, and possibly the reason that COG reached a certain point and then you couldn't take it any further. Do you see any organizational principles that maybe you couldn't see at the time that would allow you to take these lower level behaviors and stack them up in a way that really will give you the more sophisticated, strategic, longer term actions or task planning or whatever that you would like to have if you're going to have robots that are more autonomous?
Yeah, so I like to think about it slightly differently. Just like techno-humankind has fallen in love with computation to do everything, digital silicon, we've also fallen in love a bit with neurons. So let's just talk about neuroscience for a while, and then I'll generalize. In neuroscience, it's all the neurons. The glial cells, they just hold up the other cells. They're structural. Oh, they give food to the neurons. Oh, they do some signals. They do some stuff. Oh, and there's these other little molecules floating around, nitrous oxide and stuff that it signals. And it's not all electrical. It's more complex than we thought, but it's still the neurons that are stuff. So we didn't get it right. We still don't understand how it all works. But there are plenty of other systems which, to us, may not appear so interesting, but they operate without electrically operating neurons and do interesting things. Plants compete with each other. They attack. Some of them are nice to kin and not nice to non-kin. And they do it without neurons. They're doing it in other ways where the mechanisms, the mechanical, chemical stuff is doing stuff in a different way. And there are other things that play in us. We've got another neural system down in our gut, which we only communicate non-electrically with between our brain and the gut. But they communicate and interact. And you can have diseases of the neurons in your gut without having a disease in your brain and vice versa. And the system breaks down. It's more complex than we think at all times. Just like when we're going to get the human genome, and the genome is the software, and the little RNA thing that builds the proteins is the computation, and then it all works. And then we discovered most of the genome is not about that stuff at all. It's about something totally different that we didn't understand. It's about process and system. We've become a little electrocentric. We've become silicon and digital Turing computation centric in our technology, and we've become electrocentric in understanding how natural systems work. And there are other things at play. So yes, interesting, but I think it's part of a bigger, wider thing that we don't yet have good ways of talking about.
So one of the things I was discussing this week with another colleague was the idea of bio-inspired versus what you could call bio-slavish, right? So you have some people who believe that you have to try to emulate neurons and neural systems, including glial cells, including all of the pyramidal cells and all of that stuff. You have to follow them as slavishly as possible. There are other people who take the view that you have a problem on the engineering side and you're stuck. And so you look to see what the biology is doing that solves this problem. So would you say that that could represent a kind of sweet spot, that idea of do things as well as you can in the technology, and then when you have a problem or when you see something clever happening in the biology, then you go in and try and imitate that?
That's one way of doing engineering and science. Another way is to think from first principles. What are the possible ways that organization happens? How to get order from disorder, because that's what biology has done. What are those fundamental mechanisms? And we largely don't have good mathematics to understand that. There's some things from physics, but it's not quite the same as what biology does. I tend to think that assuming everything keeps going okay, just like now we look back at phlogiston theory and say, what were those people thinking? Phlogiston theory was that burning, the act of burning, is done by a common material in all the things that burn. It was phlogiston. Lavoisier and Priestley, I think, they said, no, it's not the stuff in the things that burn that's common. It's this other stuff outside oxygen that's the common element of burning. And that completely fit the data from when you burn things and you weigh stuff, what happens. And phlogiston theory didn't fit the data they had at the time, but it was so strongly held. It lasted for a long time before it got replaced. So we've got all sorts of theories, which will last for a long time. But just like now, some people look back and think, what were those people thinking with the models in the second half of the 20th century and the whole of the 21st century? So I'm prepared to think that we don't have it all right at this point. I'm much more about, let's look at everything and try. And maybe someone will get lucky. Someone, not everyone. Someone will get lucky and come up with something new.
One of the issues that we can think about as an organizing principle, or where we'd like to see an organizing principle, has to do with that issue of going from the very bottom of behaviors, the interaction with the outside world, to the planning and more symbolic, or what could be more symbolic. And in the neural world, there's a lot of argument about whether you would do all of that neurally from the bottom to the top, or whether it would make sense to get more symbolic up at the top and have interfaces between various layers that are going to pass more and more symbolic representations.
Well, by the way, that's going on with large language models right now. They're lousy at arithmetic. So people are bolting in Mathematica or something. They call that, and it does the arithmetic correctly, and then they can spout it out. So they've gone from a pure model that happens to be based on the old linear perceptrons to something which is becoming hybrid as they try to make it practical.
So do you imagine then that there's going to be a period, I don't know, maybe 10 years, maybe 30 years of...
Maybe 300.
Maybe 300, indeed. You always think long time scales in your essays. Is there going to be a period where there is just these patches and where we're essentially saying, okay, this system works best at this level, and then we can bring this in to fulfill this little function that we need? And or do you think eventually we will come up with some kind of thinking substrate that will take us from the bottom to the top?
I don't know whether it's going to be a thinking substrate, but I will say all evidence, if you look at human history and human technology implementation, we keep some things and we patch around them. Brunel, 1824-ish, figured out how to get rails laid long distances. I think the first long-distance rail was from London to Bristol, and it changed it from a 4-day journey to a 4-hour journey, something like that. And for trains, we still use rails. The principal bomber for the United States is the B-52. They were all built between 1961 and 1963. They are slated to fly until at least 2040 and maybe 2060, 100-year-old planes. The airframe is the same. The electronics inside is different. They've had a couple of generations of jet engines. They're about to get another generation of jet engines. But we always patch our technologies. We don't throw them all out. All flying jets look like 707s now. At some point, we may get a new form, but that's been around since 57, I think. We will be patching things. That's what's going to happen.
But what will we be patching? What are the cores of the technology we see today that you think we will still be using?
We ain't going to throw away silicon digital gates. And they are here. Maybe in 300 years, we won't use them anymore. Maybe it'll be like Voyager, where they had the neural
gel
packs.
Yeah.
Things will change over time, but it could take a long time. And silicon is around to stay, even though I don't think it's what brains do. I don't think it's the right metaphor for many things, but it's useful for a lot of things. And our technology will be centered around that for a long time. By the way, do you know who invented the logic gate? AND gates, OR gates, NOT gates? It was Claude Shannon.
I did not know that.
And his 1938 master's thesis at MIT. Before that, people just had electromagnetic relay circuits, and they thought about, oh, this coil pulls this switch down, but they didn't have a principled way of thinking about it. And Claude Shannon said, this is De Morgan's laws of logic. We can apply that, and he invented the logic gate. That was before he invented information theory. All these things have to be invented, and then they stick around for a long time, and then other things get invented.
Yeah, but the trick is in picking which is going to be the winners and which are...
Yeah, and in reality, if you're a technologist, you're always in a situation where there is a incumbent technology, incumbent capital investment, and you can't just throw it out and change everything. So intellectual purity, correctness is not the same as what happens in the real world, because there are other forces that can dominate.
Yes, we've covered that in the podcast before, but it's always the same example, right? VHS and Betamax always ends up being the example. Have you got a better one?
I mean, right now, the notion that we have roads, there was the Roman roads, but then modern roads were invented by Ford, so he could sell cars because his cars couldn't go on the rutted roads. And that's what we have, and so that's what we're building to.
Okay, last question, I promise. When you look at the robotics technology that you've been involved with, that you've seen colleagues and competitors involved with over the last 30, 40 years, if you could pick out one or two problems that you think we're still not close enough to solving, and I know there are probably many, what would be your top picks?
Oh, it's easy. Hands. Just nearby here at Stanford, in Margaret Jack's Hall, there's a robot that I used back in the 1970s. It's called the Scheinman arm. Rick Scheinman built it at Stanford arm. And the gripper it has is a parallel jaw gripper of two fingers that go back and forth. The company that I built, Rethink Robotics, had hands almost the same. All the robot picking solutions either use suction cups or parallel jaw grippers. Hasn't changed since they were built in the 1960s.
Now, I saw that in your essay, but I immediately had the question, what about prosthetics? We have fantastically interesting prosthetic hands that have force feedback.
Somewhat interesting. And what are they controlled by? A human. And this is a thing to look for. When you see a video of someone saying, I've got a new robot hand, and you see the video of it doing complicated stuff, you probably only see up to just below the elbow because there's a person holding it there. Go on Amazon and buy the gripper for $3. A human operating that can do fantastic manipulation, much better manipulation than any robot can do. It's the human brain that's doing it. It's not the gripper.
I get that, but from a technological, mechanical point of view, we may not be able to control the hands, but if we can make the hands, if we can give them force feedback skin, doesn't that push the problem not into the hand, but into the control?
Okay, show me where they're deployed in factories. They're not, because we don't know how to do it well enough. No, people say, but surely you can just do X and then it'll work. Well, okay, go start a company and do that. People have tried. We don't know how to do it yet. The human hand is actually a very complex thing. It's not just actuators and force feedback. There's stretching of the tendons. The skin has various properties, and when you change how your hand structures, the compliance of the skin changes, and you adapt that. You do all sorts of things with your human hands that those prosthetic hands can't do. So they're not as good.
Okay. And are there any others?
Human mobility is fantastic compared to the mobility we've got in any other systems at the moment. And again, it's because it's not just a position control system. It's compliance, it's energy storage, it's energy reuse. Some people have tried to build running machines like that, but it's very hard. The materials don't exist. No one wants to pay for them. No one wants to fund it.
Okay. Rod Brooks, thank you so much for coming on to Brains and Machines.
Thank you.
Thanks, Sunny. I love this interview. And Rodney Brooks is extremely pragmatic and focused on real application. And I really enjoyed listening to him. For more about Rodney Brooks' work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hey, guys. How you doing? Nice to be back again.
So he gives us some pragmatic view of everything, right? So in his past, he was processing 3 images and he was talking about the 10 meters in 6 hours, about the Roomba. But the thing that actually stuck with me is, but it can't play chess or something like that. So anything we do is always linked to, oh, but can he do this? Can he do that? So I have a question that might be philosophical. Is it true that at the moment, we rather think more of showing off the newer, more complex learning algorithm to solve very tiny, little complex problems rather than getting out with the next reliable, low-power, real application?
Look, I think it's an interesting perspective in the sense of, in order for the various agency to fund the field, they have to feel that the field is making progress, that we are tackling the bigger, more important problems. And I remember when Telluride Neuromorphic Workshop began, it was very much focused on the sensory processing, low-level stuff. But then there was a point when the National Science Foundation, who funds it, came to us and said, now you got to get more serious. You got to get bigger. You got to get into cognition. So at that point, the name of the workshop actually changed, right? It became neuromorphic engineering cognition workshop, and then everything switched. So I think it's natural for the field to try to tackle harder and bigger problems. But hopefully, we're not forgetting the fundamentals. And Rodney talks about that as well, the fact that one can build from basic principles, or one can build by observation of what goes on in the natural world, and both of them are important. So to answer your question, I think we still need to focus on the fundamentals, but we cannot not have our eye on the big prize. Otherwise, people don't pay attention.
Yeah, I think having known Rod and certainly watched his career through the 90s and since the 2000s, I think that going back and forward between thinking and doing sort of more academic work and actually building stuff that he has to sell, I think that really shows in his pragmatic approach. And I think it's really helped his success. I think sometimes we as academics allow ourselves to just squirrel around in the corner without actually achieving anything that's really going to make any kind of impact. And I don't think anyone can say that Rod Brooks hasn't made an impact.
Yeah, but I do think that there is maybe this is me coming from the academic perspective, there is a little bit of a dichotomy between commercial impact and scholarly impacts, right? Those are two different things. And you look at the Mark Tilden robot, for example, the Robo Sapiens and so on. I don't think we would say that made a big contribution from the understanding of robotics and improvement and so on. I do think that the Roomba is a different story. The mapping, the SLAM and everything that went into it, that was pretty amazing when it came out and continues to be. But nonetheless, I do think what happens in the lab is as important as what gets commercialized.
I think both are important. And I think the thing about Rod is he made both a commercial impact and a scientific impact. And the number of people you can say that about is not as huge as we would like to think. Sure. And also, I guess I've been thinking about this in my own small way. Obviously, my outputs are not machines or technical papers. My outputs are articles and books and things. And with this book that you and I are writing together, Ralph, it's made me realize, in my case, I'm building text, right? And I think sometimes it's very easy to just shut your eyes and say, oh, well, it'll be good enough. That's not what I want our book to be. And I think it's actually quite similar to dealing with technical problems. You can't just shut your eyes. You have to go forward and grapple with them.
Yeah, I agree with that. And that's his perspective as well of real-world implementation. So what you do in the simulation, in the environment, it's not as good as when you put it in a real world. And then you see the problems. And especially if you're selling 50 million Roombas, it better work. It still gets stuck on my chair. It does, and I have one per floor and eventually I have to go move it over. But still, overall, it better work. And that's what is really keen about seeing the kind of translation that goes from the lab to the commercial space. Millions of people get access to it. And then hopefully there's a feedback to the designers that basically allows them to improve and make the science even better.
And although I know it's nothing to do with neuromorphic or hardware or the kind of stuff that we usually end up talking about, I thought his comment about Baxter was really interesting. So Baxter, for people who remember, was this industrial robot that was designed to imitate a person. The person would show the robot what to do, and then the robot is supposed to do it. My recollection is he says that the problem was that people weren't able to show it what to do very well, so that the robot worked in some ways and it was successful as an industrial robot in that, as he said, it got the robot out of a cage. It made it possible for the robot to be working alongside humans because it was safe. But there was some human-computer interaction problems that meant that it wasn't maybe as programmable by imitation as it should have been. So I thought that was interesting, is that this dance of technology, we're always going back and forth between the hardcore spiking versus analog versus digital neurons and all of that stuff. But ultimately, if you program it in such a way that the people can't use it, it kind of doesn't matter what it's built of.
Yeah, I like the fact that his original work was inspired by insects, right? Everything was so slow and it takes so long to do an image, to move a meter and whatnot. But then insects were moving around and zipping around and so on. And that brings us back to the whole neuromorphic ethos, if you will, right? To look at what natural intelligences and natural organisms do and then try to see what are the principles that we can learn from them, and then how can I apply these principles to build machines.
Yeah, I think that was what attracted me to it. Was this bottom-up approach had a lot of analogies with the neuromorphic approach.
So talking about robots, let me put in parentheses that I'm very happy that now we know how many takes it took to get the video of the backflip. It's years that I'm waiting for this. But aside from that, he says something that we should all pay attention to, right? He said humanoid form, it's a dead end, which is very bold thinking about all of the humanoids that are coming out now. But I do agree. We should do much more targeted robots. What do you think?
I just want to say that someone who's spent a while thinking about humanoids for elder care, I do think there's a place, I think I've said this before in the podcast, I think there's a huge place for robot pets. The technology is there. I don't know why I can't buy one. I'm allergic to cats and dogs, so I would buy one tomorrow for my kid if I had the option. But I'm not sure to make you take your pills or bring you breakfast in bed or help you in the bathroom. I'm not sure that thing can be anything other than humanoid.
So I have a slightly different take on it. It doesn't have to be necessarily fully humanoid, right? So let's look at the hands, or let's look at the legs, or let's look at specific pieces that we can make really work, and that in itself has applications. I did see a video this morning, in fact, that crept up on one of my feeds, where there's this pseudo-humanoid robot that was helping somebody, a wheelchair bound, get up. So it conformed to the way the person was sitting. So the affordance was right for the person to lean upon it. And then it stood up. Then he got the person out of the wheelchair, and then he walked the person to where he needed to be. But this is a case of general care, right? You can have partially humanoid or at least humanoid adjacent type of architectures that would allow for help in the home and things of that sort. So I think there's a space for that for sure.
I want to say one more thing on this, which is that, first of all, a lot of us have the experience of not having enough space for all our appliances that we'd like to have in our kitchen. You want to have a juicer and a blender and a coffee grinder and all of these other bits and pieces. And it's one thing with apps, right? Apps don't really take up any physical space. Yes, they take storage, in your hard drive, but otherwise they're not taking any physical space. Machines are different. They physically take up space in your house. So if you are having lots of different machines to do lots of different things for you, ultimately, if you could put them all together into something that we would recognize as a healthcare assistant, then I can see the advantage of that.
I mean, point is not seeing the advantage or not, because we clearly see it, right? Like, why not having just a machine that is doing what I do? But the point is, can you make it do it? Because at the moment, if we do recognition, there's not enough power in a robot to do anything else. So another point that I have, and probably this is targeted to you, Sunny, we keep saying robot will stealing our job, okay? Or people are afraid of that. So where is the fine line to describe what is actually working and what's the good in it without creating this hype that goes nowhere?
Okay, I think this is a really important question. And it's something I've thought about a lot. As you can imagine, I've written about robots a lot over decades. And to me, controversially enough, the answer is not technology. The answer is capitalism. If you want to have arguments about whether people lose their jobs as opposed to having less work to do in their lives, it's having lots and lots of machines that are owned by very few people who do not share the fruits of those machines' labors. That's the problem. So to me, it's about politics. Inevitably, yes, people are going to lose their jobs to machines. It's happening already. It's happening in journalism, quite frankly. But on the other hand, that is part of the trajectory of life, and that's not necessarily always a bad thing. Some of the jobs that are easy to automate are the ones that are not terribly interesting anyway. I use artificial intelligence. I use Claude, as I think I've said, in my work now. I don't let it write anything. I don't do that because I'm supposed to be the writer and it all needs to be processed through my brain, all the information. But I do use it as a kind of assistant, as an editor looking over my shoulder and letting me know if I've got it right or not. And I couldn't have afforded to do that before. So nobody's lost their job by me having access to Claude, but I am then more productive. But you could end up with a situation where all of the food and all of the goods are being produced by machines, and all of the land and all of the machines are owned by a very small number of people. And then the rest of us are just animals to be moved off the land, right? We're just an annoyance, and that's where we get into the politics of it. And I think there's a real question there.
But I would also, even from the engineering perspective, I would argue that even if you had these robots running around doing these things, somebody has to maintain them. Somebody has to program them. Somebody has to set them up. It's just transference of jobs, maybe, as opposed to a replacement. It's just that folks have to change their skill set. So there's a couple of things that I want to touch on briefly that he said. He had this skeptical aspects of what is neural control, and should we be using what he refers to as only positional control when thinking about neuromorphic robotics, if you will. I don't see it as only being just about positional control. There's other features that we measure that we can compute that play a role in those control systems that also feeds into anything that we can construct in a neuromorphic system. So I think the skepticism there is, from my perspective, a little bit misplaced. And the other thing I wanted to bring out, he says that there's certain things that happen that do not include glia, do not include chemicals, and it's all neurocentric. But you look at trees, and trees are communicating together and competing and so on, and there's intelligence in that is not neuronal. But I will point out that trees also operate on a very different timescale. So timescales matter. If I want to do something that is reactive, that is quick, that is responsive, that does not fall on when helping Ma, those are going to depend somewhere on neurons and some kind of equivalent thereof. So we cannot always depend on these other supposed intelligences that operate at a very slow time scale. And then the prosthetics that he talked about, that, prosthetic, there's always a human in the loop. That human is what's making decisions and whatnot. Again, that's a little bit old school. The newer school ones have autonomous, semi-autonomous components where when you're about to grab that cup, you're not moving every single finger to go grab that cup. You look at it, you say it's a cup, and the hands conform and come to the cup, close all by itself. So that has to operate. That's where that closed loop with synthetic skin and sensors in the skin at the fingertips plays a role. And that can be all entirely within the prosthetic itself. So the prosthetic doesn't always include the human. That's all I'm trying to say, is that there is intelligence within the prosthetic itself that one must also acknowledge.
And you could argue also that the intelligence that it takes for the prosthetic to understand the intentions of the user is very real intelligence. So yes, I agree with you that he sold short how much progress we've made in hands, because he's looking at the robotic side where you can perhaps be a lot more, as Giulia said, pragmatic. If you know exactly what it needs to do and you don't really care what it looks like and you don't care about the flexibility, then why bother with something that looks like a human hand and that has that kind of dexterity? But if you need something that has to be flexible in the sense of adaptable and changing what it's doing all the time, then maybe you trust that nature has a configuration that's really going to give you all of the functionality that you need over a lifetime.
So I think this is a great place to stop. Thanks, Sunny, for this great interview, and Ralph for your valuable insights as usual. In the next episode, Sunny will be talking to some of the research and development team at the California-based artificial intelligence company Bains. We hope you will join us then.
That brings another episode of EE Times to its end. Thank you for listening, and thanks to our guest, Professor Rodney Brooks. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript, along with direct links to the other stories we've mentioned and other resources. Thanks for listening.